Hello. Here we have an electron in a variable electric field, and they give you the electric potential in the region of space as a function of x, and that's about it. That's the description of this problem. On the other hand, I need a diagram in which to help me think about what's going on, especially when they ask a number of questions that that relate to this field. But I do need a visual hook. So before we get into the problem, let's go to the slide where I blew up my diagram. So this more or less explains what's going on. So we have two charged plates, a negatively charged plate on the left and a positively charged plate on the right. And notice that one's a little bigger than the other in terms of how their arc. But the way those charges are configured on those curved surfaces gives you this electric field that appears to converge as you move along the x-axis to the right and diverge as you move along the x-axis to the left. Now, what I'd like to I want to point your attention to what's going on to the left of the negative plate. And this may explain why the electric field is 0 at negative 1.75 meters, especially at a later time. The positive plate here to the right, its field extends beyond the negative plate. So that's what that indicates. And then the negative plate, its electric field extends into it. And the combination of those two, they do add, they'll cancel to some extent, but at negative 1.75, they cancel, and the electric field is 0 at that location. Okay, and I'll explain more precisely how that came into being. All right, so do we have a picture of this electron feeling a force, experiencing a force that's directed to the right, and so will be the direction of the acceleration to the right, at least within those, between those two plates. All right, let's go back to the problem. An electron starts at rest at x equals 0 and travels to x equals 20 meters. Calculate the magnitude of the work done on the electron by the electric field during this process. I'm going to start with the definition of electric potential equals negative work per unit charge. Solving for work, that equals the change in potential times Q. So all you need to do at this point is substitute 20 in for x, evaluate the potential, electric potential function for 20, and then subtract that for the electric potential function evaluated at 0. The little algebra, multiply that by negative 1.602 times 10 to the negative 19, and we have a negative sign there, and that is where you get a positive 1.5 times 10 to the negative 16 joules. Okay, moving right along. There's the big diagram. Okay, part 2 of A, calculate the speed of the electron at x equals 20 meters. We're going to apply the work energy theorem and associate the work done by the electric field to the gain in kinetic energy by the electron. So the work that we calculated earlier will equal 1/2 mv squared. I don't know if I need to say any more about that. The rest is just plug and chug in algebra. All right, part B, derive an equation for the x component of the electric field as a function of position x. I'm a big fan of memorizing, well, some equations, not all of them, but the definition of potential equals ED. And then solve for E, and although this appears in the equation sheet that you'll be given, the electric field, especially when you have a variable electric potential, is the derivative of the electric potential function. So taking the derivative of the electric potential function, we get negative 4x minus 7. So where the electric field is 0, okay, you can set this equal to 0. That's where I got the number negative 1.75. Just setting this equal to 0 and solving for x. Okay, so that'll come up at a later time. So the electric field is directed to the left at x greater than negative 1.75. Okay. And then at x equals 1.75, the electric field is 0, but a little bit to the left of negative 1.75, the electric field, or at least the electric force, will be directed to the left, and the electric field will be directed to the right. Okay, sounds like a lot. It is. All right, part C. On the axis below, sketch a graph of the acceleration of the electron as a function of position x. Start with the definition to get an idea of what this graph is shaped like. I just can't assume it's linear or a constant. It is linear, but not a constant. Let's start with the definition of the electric field. Electric field is force per unit charge. F equals ma. Solve for A, we get EQ over M. Now, since the electric field is a linear relationship, it has a slope, we are going to draw a line on the acceleration graph that shows an upward trend. And since it's the acceleration, even though the electric field is directed to the left, the acceleration is directed to the right, hence a positive slope. Now notice that I started on the a-axis above 0 for the simple reason that at x equals 0, the electric field has a value of -7. So it's going to have an initial acceleration directed to the right. Okay, moving right along. On the axis below, sketch a graph of the kinetic energy of the electron as a function of position x. Let's get an idea of what the shape of the graph is. So we're going to start with work equals electric potential times Q, which is equivalent to the kinetic energy. Now notice that our electric potential function is a quadratic. So I'm assuming that if the electric potential function is a quadratic and we're just multiplying by a constant, the fundamental constant, the charge on the electron, then so is the kinetic energy function. So I'm going to draw a graph that resembles a quadratic. Okay, as you see there. Moving right along. Part D, at which of the following locations will an electron that is released from rest move in the negative x direction, so to the left? Check all that applies. Well, if I start with -2 meters, I get a positive electric field. So that means that the electric field at -2 is directed to the right. And remember, the electron moves opposite the direction of the electric field. So if the electric field is directed to the right at -2, that means that the electron is going to move to the left. So that's definitely an answer. If you substitute +1 in for x, you're going to get a negative value for the electric field. So at +1, +3, the electron is going to move to the right. So -2 is the only answer that makes sense. So again, going back to the idea or the location where the electric field is 0, that's the tipping point between the electron moving to the right and to the left, and the direction of the electric field being directed to the right and or to the left. Okay? Gosh, you have to draw a diagram. I told you, you need a diagram in order to explain this. Okay, moving right along. Oh, last but not least, part E, yay. A charged object generating its own electric field given by E as a function of x. Okay, 7 volts per meter. So it's just a constant value. Is introduced in the region. What is the potential difference from x equals 0 meters to x equals 20 meters caused by the combination of the original electric potential, okay, and the electric field of the charged object? So we're going to commingle these electric fields, the charged object's electric field with the potential difference. So this involves superposition principle. So we're going to add these electric fields up. So definition of potential difference, especially if you have variable electric field is the integral of Ex dx. So E1 plus E2, negative 4x minus 7 plus a positive 7, we get negative 4x. So the net electric field, that's what's going to be taking the integral of the net electric field, valuing from 0 to 20. You know the drill in taking an integral of the polynomial. Substituting 20 in for x, and then subtract from 0 for x. Pretty straightforward. We get 800 volts. So there's the explanation of this free response question, and it comes down to this diagram. So if you can come up with a better diagram than I did, knock yourself out, and I'd love to discuss it with you. But again, I need context. I'm a visual learner, and what helped me tremendously in understanding this problem was coming up with a possible scenario, at least a visual scenario for what's going on. All right, enjoy the rest of your evening, or day for that matter.